Assalamu alaikum to you all. Uh, so far in this course, we have discussed two main design algorithm design techniques, namely the divide and conquer, as well as the dynamic programming techniques. So today we are going to start with the last main algorithm design technique that we said we will learn in this course, namely greedy algorithm design technique. As with the dynamic programming, we have two lectures actually on greedy algorithms, and this is the first one. And this is the outline of the lecture. First, we shall define what is greedy algorithm, and then, as we did with dynamic programming, we shall learn about this design technique by example. So we're going to take our first major example in this lecture, which is called activity selection problem. Now we're going to solve this problem in detail, initially attempting to follow the steps that are normally followed in dynamic programming approach, just to show you how this design technique compare with dynamic programming technique. Okay, so we shall first of all characterize an optimal substructure for this particular problem, and then we develop a recursive solution. So this sounds like we are following dynamic programming, because actually the two algorithms are similar, but greedy tries to take advantage of what is called greedy property to make the process much shorter and therefore more efficient. So up to now they seems to be the same, but after developing the recursive solution, we shall make what is called a greedy choice. Instead of trying to solve the sub-problems before we can decide which selection to choose, in greedy strategy, we just make what is called a greedy choice. However, we must show that the greedy choice that we have made is safe. What does that mean? It means that it will lead us really to an optimal solution. Okay, the greedy choice you normally make, you must show that it will lead to an optimal solution. So this is what is called showing that the greedy choice that you have made is safe. So once we are satisfied with the greedy choice we have made, we shall develop a recursive greedy algorithm to solve this particular problem. And in our final step, we shall convert that recursive algorithm to iterative version. As we know, iterative algorithms are usually more efficient than their recursive counterpart. So usually after you obtain a greedy algorithm using recursion, normally you attempt to convert it to iterative version. So these are the steps that we will follow in solving this example, but then we will show you in detail what is typically followed actually in solving a greedy strategy. You don't have to follow all of these steps. We are following them in detail just to show you how greedy algorithms relate to dynamic programming. But actually, there's a shorter path that you can follow if you are trying to solve a problem using a greedy strategy. So we shall explain in detail again the main elements of greedy strategy. Okay, so in the final part, we will try to compare between greedy and dynamic programming strategies by taking an example, because sometimes it may appear to you that you can use greedy algorithm. It turned out to be that you cannot. Okay, right. So this is our agenda for this particular lecture. Let us start by defining what is greedy algorithm. Okay, like dynamic programming, a greedy algorithm again is used to solve optimization problems that require finding either a maximum or a minimum. Okay, so they are very similar in that respect. The idea here is that dynamic programming can be an overkill sometimes. What does overkill means? It is like, for example, trying to kill an ant with a very large hammer. Take a large hammer and hit an ant just to kill it. You could have just used your finger to kill it if you wish to kill it. Okay, so this is what is called overkill. In other words, dynamic programming usually involve very much elaborate steps. As you know, we have to solve all the options in solving a problem before choosing a particular one. So greedy is saying, no, you don't have to do that. You can just look at the situation and choose what is called a greedy choice without the need to solve the sub-problems. Okay, so in that case, the greedy algorithm usually involve less amount of work. That's what we are saying here. Greedy algorithm tend to solve problems with less amount of work compared to dynamic programming. Okay. Now, however, they have similarity with dynamic programming. The problems that you will solve with greedy algorithm, they also exhibit the optimal substructure. Just like the dynamic programming, the problem must exhibit optimal substructure before you can apply both dynamic programming as well as greedy algorithm. However, for problems that you can solve with greedy algorithm, the next important property they satisfy is that they exhibit what is called greedy choice property. So this is the difference. It's not all dynamic programming problems that you can solve with greedy. Only those for which you can only those that exhibit greedy choice property. Okay. What does greedy choice property means? It means when we have make a choice, or when we make a choice at each step in solving the problem, we should simply make the one that look the best at the current time. That is to say, we make a locally optimal choice in the hope that it will give us a globally optimal solution. That's the idea. In the case of dynamic programming, we don't allow any uncertainty. We have to solve all the options possible at any particular step and then choose the best one. Okay, but in greedy, we will say, no, we don't have to solve all those sub-problems before we determine the best one. No, we're going to look at the current situation and see which one do we think will give us the best answer at the current time or in this particular step. That's what we mean by locally. Okay, we make that choice in the hope that eventually it will lead us to a globally optimal solution. That is to say, it will solve the problem entirely in an optimal way. Actually, this is not new strategy for us. We have seen it in the data structure course. We have solved at least two problems using greedy algorithm, only that we didn't mention at that time that we are using greedy strategy. If you recall the discuss shortest path algorithm, what we were doing at each step, we choose among the costs that we have, we choose the minimal one, okay, hoping that it will lead to an overall minimal solution. So actually that discuss algorithm is an example of a greedy algorithm. Similarly, the Kruskals algorithm for finding minimum spanning tree. Again, if you recall, what we did was we sort the weights. We sort the edges of our graph that we wish to find its minimal spanning tree. We sort them based on weights, and then we start by choosing those that are the smallest. We add them to our resulting graph, provided they don't form a cycle, and then choose the next one, see if we can add it without making a cycle, and so on. So in other words, at each point in solving Kruskals, we were choosing we are making a greedy choice by choosing the edge that has the smallest weight. This is the idea, and we're going to see it more clearly when we take an example in this lecture. Okay, so the final point to make is that greedy algorithms don't always yield an optimal solution, because what you are saying basically is you are more or less like gambling, but not really gambling, because you are making the choice based on some attribute that you can see of the problem. Intuitively, you think if you take this, it will lead you to an optimal solution. So that may or may not work. Okay, as we shall see again when we do the comparison towards the end of the lecture. We're going to take another problem to see whether a type of that problem can be solved with greedy, another version of it cannot. Okay, so it may not always yield an optimal solution, but if they do, they are certainly going to be more efficient than the dynamic programming approach. And this is the main thing. Okay, so to explain exactly what greedy algorithm strategy means, we're going to take an example. And that example is called activity selection problem. Okay, so the idea here is, let's say you have a particular resource. Let's take, for example, in case of our Jubel University College, we have the MPH, which is a large hall that is normally used to hold activities. The activities could be student activities from different clubs that we have, student clubs, or it could be faculty lecture, it could be examination, and so on. So you have this list of activities that you want to hold in a particular day. Some of them may be competing with each other because they clash in time. Okay, and the question is, how do you select the activities to approve? Okay, so many of these organizers, they apply to use the hall, and let's say you are the one in charge of approving the use of the hall. So how do you approve these activities in such a way that you allow the maximum number of activities possible? Okay, of course, the ones you choose must be what is called compatible. They must not clash in time. The activities that you choose must not clash in time. Let us specify the problem more clearly. It says, suppose you have as input a set S of n activities, okay, to be done in a particular place or a hall. Let's name the activities A1, A2, and so on until AN. Okay. Each activity has a starting time and a finishing time. It says activity AI, assume it starts at time SI and it finishes at time FI. Okay, we're going to assume that activity I will run during the half open time interval from SI, including the SI, until FI, but not including the FI. So this is to make sure that each time interval is actually distinct. It doesn't clash even for a second with another activity. Okay, so suppose you have this. Okay, let's also define what we mean by compatible activities or mutually compatible activities. So two activities are said to be compatible or mutually compatible if their intervals do not overlap. Okay, so that's the idea. So with this input, what output do we need? Okay, we want a subset of S. We want to choose a subset of these activities which has the maximum number of mutually compatible activities. So we want to select as many of these activities as possible, but we want to do it such that the ones we choose do not overlap. They are mutually compatible. Okay, this is basically the problem. Now we note that although we stated this problem in terms of the objective of finding the maximum subset, okay, there are other ways we could have defined the problem with a different objective. For example, we could say choose the activities that will utilize the room for the longest possible time. Okay, so that could be another objective, but that's not the objective in this particular case. Okay, so here, if you choose this longest time, even if you have one activity that will take the whole day, then that is the one you choose, rather than choosing small activities that will take only half an hour and so on, and overall you use very little time. Okay, this is the difference between this objective and the one we have stated here. Another objective could be, suppose the activities are not for free. Yani the scheduling of activities in the room is not for free. Each organization must pay a certain amount. Okay, so another objective could be, choose activities that will give you the maximum income in terms of the fees, the rental fees. Okay, so just to show you, activity selection problem can have different objectives. Okay, but in this case, our objective is simply to choose the maximum number of activities. Okay, a maximum subset of S that has mutually compatible activities. This is our target. Okay, now we're going to assume that the activities that we have in this set S, they are sorted by finishing time. Sorted by finishing time. So activity 1 will finish before activity 2, and activity 2 will finish before activity 3, and so on. So they are not just random. We have sorted them according to finishing time. Let's take an example just to again clarify what does activity selection problem actually means. Okay, so this is an example. Suppose you have this 11 activities to be done, and these are the starting times and these are the finishing time. Okay, so for example, for activity 1, it will start from hour 1 until hour 4. Okay, assuming you call the time intervals in terms of hours. Okay, notice that activity 1 finish at 4, okay, earlier than the finishing time of activity 2, earlier than, and so on. Okay, so this is what is called monotonically increasing order. I will use the word monotonically in a number of places within the lecture. I would like to just explain what does that mean. Monotonically increasing simply means non-decreasing. Okay, non-decreasing sequence. In other words, the next item or the next element may be equal. Okay, not strictly increasing. Like here, you see, activity number 5 is finishing at 9. Activity number 6 is finishing also at 9. This is not a problem. Okay, what we don't want is the next activity to finish before this one. Okay, so monotonically increasing simply means a sequence that is not decreasing. The next item may be either bigger or the same. Okay, this is the meaning of monotonically increasing sequence. So the activities in the activity selection problem, they are sorted, as you can see here, in monotonically increasing order. Okay, now can you identify some of the activities that are mutually compatible? I have some examples here. Okay, A3, if you look at it, start at 0 and finish at 6. Okay, it is therefore compatible with A9 because A9 start at 8. Okay, so there's no overlap. This one finish at 6, this one start at 8, and then it finishes at 11. And then A11 start at 12 and finishes at 16. So again, you can see that there is no overlap. This one finishes at 11 and this one starts at 12. So this set is a subset of mutually compatible activities. However, this is not a maximum subset, so this is not an optimal solution. We want to maximize our choice. Okay, now here are two examples of maximum subsets. You can see these two subsets, they have 4 elements. So this is another point to note actually. As we know, optimization problems, the solution doesn't have to be unique. Okay, so we have 2 subsets that have maximum number of elements 4. Okay, so A1, as you can see, actually it's better for me to explain to you this example diagrammatically. They say a picture is worth 1,000 words. So let's look at these examples in the next slide, where we actually state the activities in terms of time interval, so you can see it visibly what does each activity actually covers. So activity 1 start at 1, as you can see, these are the time intervals. So it starts at 1 and finishes at 4. Okay, activity number 2 start at 3. Okay, you can see this is 3 and it finishes at 5. So starting time is 3, finishing time is 5. Activity number 3, on the other hand, start at 0, okay, and finishes at 6, and so on and so forth. So these are our activities. The question is, where are these activities that we say will be mutually compatible and actually will give us the maximum subset? So A1 clearly is here. It finishes at 4. Okay. A4, 1, 2, 3, 4. So A4 is here. You can see it's clearly compatible with this one because this one finishes at 4, but this one starts at 5. Okay, so A4 is compatible. Okay, then we have A8. Okay, A8 start at 8. So you can see this is the A8. Okay, and finishes at 11. Okay, so it's also compatible with this one. This one finishes at 7. This one starts at 8. No issue. Okay, and the last one is A11. The last one here, which starts at 12. Okay, this one finishes at 11. This one starts at 12. Okay, until 16. So that gives you 4 activities that are mutually compatible. This is one of the optimal solutions. Another optimal solution is A2, A4, A9, and A11. Okay, you can see A2 finishes at 5. Okay, then A4 starts at 5. Okay, so this is the A4, it starts at 5. Clearly it is mutually compatible, because remember what we said, the time interval, even though this one stops at 5, actually it stops at 5 but not including the 5. But this one will start at 5, so they are actually mutually compatible. Okay, A9 will start at 8. So like now activity number 8 also starts at 8. This is actually number 9, it also starts at 8. So again, this is compatible with A4. Okay, this one finishes at 7 and this one starts at 8. Okay, and finally activity number 11, as we discussed earlier, it starts at 12. So even though this one finishes at 12 but not including the 12, so it is compatible with activity number 11, and so on. So here we are with two subsets with the maximum number of mutually compatible elements. This is what we want to find out. Find one of the optimal solution, but we want to do it systematically with an algorithm rather than by inspection. Okay, this is the idea of the activity selection problem. Okay. So we're going to follow the sequence as we said at the beginning by first of all characterizing the optimal substructure of the problem. So to do that, we start by defining a notation. We define a set Sij to be the set of all activities AK in the overall set S, okay, such that the finishing time of activity, rather the starting time of SK is after, that's what we mean by greater than, so SK is greater than Fi, so the starting time of our activity here AK is after the finishing time of activity I, and the finishing time of our activity AK is before the starting time of another activity AJ. Okay, it's better to show this diagrammatically, so let us show what we mean. So here is our set of activities S, all the activities. Now a subset Sij is the set of all activities that their starting time is after the finishing time of AI. So that's why we got the subscript here I. All activities in Sij, they start after the definition of activity AI, but they finish before the starting of the activity AJ. Okay, so you can see all the activities inside this set, their finishing time is before before the starting time of AJ, which is SJ. Okay, so this is the time interval for activity AJ from SJ to FJ. And this is the time interval for activity AI, SI to FI. So our subset Sij will be all activities that starts after AI finishes and finish before AJ starts. Okay, so that is our term here. Suppose we have this subset. Okay, obviously activities in Sij are compatible with all the activities that finishes before Fi. They are compatible with AJ for AI, for example. Okay, any activities here on the left side will be compatible with the activities in our Sij. Similarly, they will be compatible with activities on the right side here. Example AJ. This is just an example. There could be many other activities to the right. So all the activities here are compatible with those before this Fi and those that start after or that start at Sj and so on. Okay. Now suppose we wish to find the maximum subset of mutually compatible activities in our subset Sij. Okay, and let us suppose that Aij is that particular maximum subset. So let Aij be such a maximum size set of mutually compatible activities in Sij. Let us further assume that this optimal subset contains an activity called AK. So AK belongs to Aij. Now by putting AK in Aij, it means we have actually split the original problem of finding the maximum subset of mutually compatible activities in Sij into two subproblems. Okay, the two subproblems are finding mutually compatible activities in Sik. And remember, by our definition of our notation here, the set Sik means activities that start after AI finishes and finish before AK starts. Okay, so that will be on to the left of the AK. We also need to find mutually compatible activities Skj to the right of AK. Okay, activities that start after AK finishes and that finish before AJ. Okay, so these are, if we put AK to belong to this our presume optimal solution, then by putting it there we have split the problem into two. To the left of AK, finding the mutually compatible activities in Sik, and to the right of AK, which means finding mutually compatible activities in Skj. And obviously, for us to have an optimal substructure, the solution to these two subproblems must also be optimal. Okay. Now let us define Aik to be an intersection of our optimal subset Aij with the set to the left of AK, which is Sik. Okay, that means the activities in Aij, the optimal subset, that finishes before AK starts. Let us also define Akj to be the intersection of the optimal subset Aij with the set of activities after K, so skj. Okay, so this will be the activities in our optimal subset Aij that starts after AK finishes. If you do that, then you can say your optimal subset Aij, okay, is actually a union of AIK and the AK and the union again with AKJ. Okay, and that means if Aij is equal to this union, it means the number of elements in Aij must be equal to the number of elements here in AIK plus the number of elements here, okay, in AKJ, plus of course the AK itself, so plus 1. All right, now we want to claim that the solution Aij include optimal solution to the two subproblems SIK and SKJ. In other words, we are claiming that these two subsets AIK and AKJ are actually optimal solution to their individual subproblems SIK and SKJ. Okay, if we can show that, then it means our characterization here of the optimal solution actually satisfy the optimal substructure property. Okay, remember the definition of optimal substructure, that optimal solution must contain optimal solution to subproblems. So if these two are optimal, the AIK and AKJ, it means this optimal solution contain optimal solution to subproblems, and therefore it exhibits the optimal substructure property. This we have to prove. Okay, so this is the proof, and we're going to do it by the usual cut and paste argument. We will show that we will show the proof using just one of the two subsets, which is the SKJ. The proof for SIK obviously will be symmetric. So suppose we could find another optimal subset, A'Kj, of mutually compatible activities in the subproblem SKJ, which has more elements than AKJ. Suppose we can find another one that has more elements. Remember, our target is to find the maximum subset. So suppose there is a maximum subset which has more elements than what we assume to be our maximum subset for the solution on the set on the right side of AK, which is SIK. Okay, we're going to try to show that this cannot be true. So it's a kind of proof by contradiction. So suppose that is the case. Then it means instead of using AKJ in the solution to our main problem for the Sij, we could substitute this solution. Okay, and that will result in a set that is bigger than our mutually compatible subset. Yani if we substitute here, instead of using AKJ, we use A prime KJ, which is bigger than AKJ. Okay, then by the time we add the elements in the number of elements in AIK plus that plus 1, we're going to get a bigger number compared to what we had before, which was the number of elements in AIK plus the number of elements in AKJ plus 1, because this set is bigger than this set. So that means we are able to find another subset with more elements than our optimal solution, and that will be a contradiction. We cannot have more elements than what we presume to be the optimal solution. It means, therefore, what we suppose here cannot actually hold. So there is no such element that will have more elements than AKJ. There is no such subset, rather. Okay. So since this will lead us to a contradiction, it means that Aij is actually optimal, and the solution to the subproblems are themselves also optimal. In other words, Aik and Akj are also optimal solution to the two subproblems. So this is the normal cut and paste argument to prove that our characterization actually satisfies the optimal substructure requirement. Okay, so according to our sequence, therefore, we're going to move to the next step, which is to develop a recursive solution based on our optimal characterization. Now, since the solution Aij must include optimal solutions to subproblems Sik and Skj, we could apply dynamic programming. Okay, and as you know, in dynamic programming, we try to find a recursive solution. So let's attempt to do that, although we'll not go through with actually obtaining the solution to it. Instead, we will see how we can do it with greedy approach. So we're going to define another term. Let Cij be the size of optimal solutions for Sij. Okay, so this is just the number of elements in the maximum subset that we can get from Sij. Then it means Cij will be equal to Cik plus 1. All right. Now the issue here is we don't know the exact value of k. Okay, we are just assuming that there is an element ak in the optimal solution of Aij, of the set Sij, which is the set Aij. Assuming there is such an element, then we can say that the number of the elements will be equal to the number of elements in Sik, which is Cik, plus the number of elements in Skj, or in the optimal solution of Skj, which is Ckj plus 1. Now, here, if we were to solve this problem with dynamic programming, what we could do is now go ahead and look for all the possible options for the value of k. So our definition for Cij becomes, if the set Sij is empty, of course, we will return 0. But if it is not empty, then we have to vary k across all the elements of Sij and find the one that will give us the maximum. This is what we will have done with dynamic programming. But we're not going to do that because we want to solve this problem with greedy approach. Okay, so that's what we are saying here, that we could then develop a recursive algorithm and memorize it, or develop a bottom-up algorithm to fill in the table entries, trying to solve the problem using dynamic programming. However, instead of that, we're going to look for the greedy approach. So this is where our comparison with dynamic programming stops. We're going to now see how to solve this problem using greedy approach. And what we do in greedy approach is we make a greedy choice. Okay, instead of trying to look for all the options, now we look intuitively and select which option do we think can give us the best solution at the current time. Yeah. So instead of solving sub-problem first, we choose a solution that looks optimal initially and add it to the optimal solution. Then solve the sub-problems to find the rest of the optimal solutions. Now, for the activity selection problem, can we get away with considering only the greedy choice? Okay, the activity that leaves the resource available for as many other activities as possible. Intuitively, this will be our greedy choice. If we can find an activity that will leave more time for the rest of the activities, then it is likely that at the end of the day we will have more activities chosen. Okay, so the question is, which activity will leave the resources available for most of the remaining activities? Obviously, it is going to be the activity that will finish first. That's the answer. The first activity to finish, remembering that we have sorted our activities based on finishing time. So it means if we choose the one that finishes first, it is likely to leave more time for the rest of the activities. And in that way, we are likely to get an optimal solution. Okay, so this is going to be our greedy choice. Okay, so here, since the activities are sorted by finishing time, just choose activity A1. Okay, so instead of the dynamic programming approach where we look at all possibilities and then choose one, this one is saying, look, activities are sorted according to finishing time. All right, it is likely if we choose the one that finishes first, which is A1, then we will be able to leave more time for the rest of the activities, and therefore eventually we will be able to select more activities. Okay, so this is how we're going to solve it rather than trying to look for all possible options. So we're going to assume A1 is going to belong to the optimal size subset among the optimal solution. Now once we choose A1, that leaves us with only one sub-problem to solve. And the problem will be finding the maximum size set of mutually compatible activities that starts after A1 finishes. Okay, basically we're going to concentrate now on the rest of the activities. Okay, those that start after A1 finishes. Now we don't have to worry about activities that finish before A1 starts. Why? Because remember, F1 is the first activity to finish. And we know that S1, the starting time of F1, is definitely less than the finishing time of F1. And therefore, there is no activity AI that has the finishing time before F1. Okay, so we don't have to worry about all the activities that start before A1. Starting is not the issue here, it's the finishing time that is the issue. Okay, so it is safe, therefore, to take A1 as belonging to the optimal solution. Now, since we have only one sub-problem to solve after choosing A1, we can now simplify our notation. Instead of looking at it as having two sub-problems, we will assume we have only one sub-problem, so our notation will change. We're going to define a set Sk to be equal to the set of all activities that start after AK finishes. Okay, so consists of sets, other activities AI belonging to the set S, for which the starting time is greater than Fk. Okay, this will be the remaining problem that we need to solve. After choosing A1, so we will be concentrating with only those activities that start after A1. So generally, after we choosing AK, then we will be concerned with only the activities that starts after AK finishes. Okay, so that's how we now define our set. Instead of using the original notation of Sij, where we will have two subproblems, now we just use Sk. So Sk is the set of all activities AI whose starting time is after the Fk. Okay, this is after we have chosen AK to be among the compatible solution. Then we are left with now only one subproblem, the problem of finding mutually compatible activities in Sk. Okay, so making greedy choice of A1 implies that S1 remains the only subproblem to solve. Okay, based on our notation. Remember, S1 will be the set of all activities that starts after A1 finishes. Okay, which means after F1. Now, by optimal substructure, if A1 is an optimal solution, then an optimal solution to the original problem will consist of A1 plus all activities in an optimal solution to S1. Okay, right. So, but we need to prove that A1 is always part of some optimal solution. In other words, the greedy choice that we have made, we need to show that it is safe. So that's the next step. Show that the greedy choice is safe. And for that we have a theorem. It says if Sk is an empty set and AM has the earliest finishing time in Sk, then AM is included in some optimal solution for Sk. In other words, we can rely on AM as an optimal, it's going to be a member of the optimal solution. So we're going to prove that. So let AK be an optimal solution to Sk, and let AJ have the earliest finishing time of any activity in AK. Now we're going to try to show that either our AM is equal to AJ, or we can substitute AJ with AM in the set AK. If we do that, it means the choice of our AM is always safe. Okay, so we say here, if AJ happen to be equal to AM, then we are done. Okay, that AM has the earliest finishing time in Sk. But suppose it is not. Suppose AM is not equal to AJ. Let A prime K be the same as the optimal subset AK, but with AM substituted for AJ. Okay, remember we said AJ is the earliest activity to finish in Sk. So suppose we replace that AJ with AM. Okay, so it means our optimal subset A prime K will be the original optimal subset AK minus the AJ but plus AM. We are substituting AJ with AM. Okay, now we're going to claim that the new optimal subset A prime K contains compatible activities, mutually compatible activities. In other words, the activities inside here are disjoint, or they are compatible. Okay, proof. We know that FM, the finishing time of AM, is less than or equal to the finishing time of fj. Okay, so because fm is less than or equal to fj, the activities in a prime k are disjoint. Because they were disjoint in AK. Okay, AK we say was an optimal solution, and all we are putting now is AM. But AM has a finishing time earlier or the same as FJ. Therefore, the elements in A prime K are definitely going to be compatible. And this proves our theorem. Okay, that if we choose an activity AM that has the earliest finishing time, then it must belong to some optimal solution. Okay, yeah. So the greedy choice we make in this case by choosing the first element, the first activity to finish, is actually safe. It's going to definitely belong to our optimal solution AK, or it will belong to some other optimal solution A prime K. Either way, it belongs to some optimal solution. Okay. Yeah, actually this is the final point to note. Since the two subsets are the same elements, the same size, we can conclude that A prime K is also an optimal solution to SK. Okay, and it includes AM, and that proves our theorem. So now we need to explain how to actually go about solving greedy problems, because what we have done so far was we were following the dynamic programming approach. Okay, starting by characterization, coming up by recursive algorithm, and so on. But actually what we have just seen from the last slide is that we don't need the full power of dynamic programming to solve this problem. We don't need to work from the bottom up. Okay, instead all we have to do is repeatedly choose an activity that finishes first. Keep only the activities that are compatible with that one, and repeat the process until no activity remains. Okay, we can work top down, not necessarily bottom up. We just need to make a choice following this our criteria of choosing the first one to finish, then solve a sub-problem with the remaining sub-problem. There's only one sub-problem remaining, so we solve it. We don't have to solve sub-problems before making a choice. Okay, so now we're going to show you the recursive algorithm that will solve the original problem based on the greedy choice that we have decided on. Okay, this is the recursive procedure. I will explain it in detail. As you can see, it takes some argument. I will first explain the arguments, then we look at the code in detail. So the procedure, recursive activity selector, it takes the following parameters: two arrays S and F, which of course will be containing the starting and the finishing times. And here we are assuming that the elements in F, the times in F, are sorted in monotonically increasing order. Okay. Now the index K, the parameter K is the index of the current subproblem. Index of the current subproblem. And the number N is the total number of activities in the subproblem. Now here K actually, initially we're going to assume it is 0. So the initial call to the recursive call here, to the recursive method here, is sf0. 0, n, where we're going to assume there is some fictitious activity, A0, okay, whose finishing time is 0. Because if you do that, it means the S naught will be equal to the entire problem, the original problem we are trying to solve. Okay, so if you assume there is some fictional activity A naught, then you can divide the problem S into your A naught and S naught, where S naught is the whole set S that you are trying to solve. I hope that makes sense. Okay, so if you can solve this problem S, it means we have solved the original problem. Okay, so here K means the index of the current activity, where we're going to assume the current activity start at 0. Of course, we know there is no such current activity 0. Activity start from 1. But that will allow us to say the remainder of the problem is the entire original problem S. Okay, so S naught is going to be S. Good. Now let us look at the code. What it does is it defines a variable m initially equal to k plus 1. So you can imagine, since k initially is 0, the first value of m is actually 1. Okay, so let's look at the loop. The loop says while m is less than or equal to n and the starting time of m is less than the finishing time of the current activity, increase m by 1. In other words, we're going to go through all the activities starting from m, trying to find another activity that is compatible with the one that we have just chosen. Because here you see we are going to choose am. Initially m will be 1, as we said, so we're going to choose a1 and we are trying to find another activity, that the next activity that is compatible with that am. So obviously if the starting time of am is less than the finishing time of our fk, then it is not compatible. We have to increase m to the next one. So keep increasing m by 1 until you find an activity that starts after the finishing time of the current activity. Okay, so when you do that, the loop will stop. Okay, it means you have found another activity that is compatible. So we check after this while loop if we were able to successfully find an m that is less than or equal to n. Then we are going to make a recursive call starting from that m and add whatever you get to your set am. Okay, on the other hand, if this loop was not able to find an activity m that is less than or equal to n, it means we have actually finished all the activities, so we simply return an empty set. So basically the while loop, as I explained, it will check all the activities after ak plus 1, ak plus 2, and so on until an, until it finds an activity am that is compatible with ak. Okay, in other words, its starting time is after fk. If the loop terminates because am is found, then we're going to recursively solve for sm and return this solution along with the am. That's why we're taking the union there. However, if the loop never finds an activity am, that is m turn out to be greater than n, then we're going to simply return an empty set. This is basically what I was trying to explain there in the algorithm. Okay, I will explain this algorithm in detail, more graphically in the next slide. But before then, let's talk about the running time. Okay, the running time is going to be theta of n, simply because each activity is examined only once. Okay, assuming that activities are already sorted by finishing time. Okay, if the activities were not sorted, then of course you have to sort them using some kind of priority queue. So in that case, the running time may go until theta of n log n, especially if you are using mini heap. Then you are only going across the height of the tree to move the highest priority element to the top. So so that will just be log n, and since we're going to do that for each element, we will end up with n log n. Okay, but here we started by assuming the activities are already sorted and we are examining them one after the other. Therefore, the running time is not going to be more than theta of n. Okay, now as I said, let us see this solution diagrammatically. Maybe it will help to explain that particular recursive routine. So what we are saying is, suppose you choose A1. Okay, then all we have to do now is loop through the activities from 2, 3, and so on until we find one whose starting time is after the finishing time of A1. So obviously, if you look at A2 here, its starting time is before the finishing of A1, so we're not going to accept it. Okay, so our M will not be 2. Next, we increment M to this one, 3. Also, clearly, the starting time of this one is not before the finishing time of this one. So this will also be rejected. Okay, so I have highlighted these 2 in blue to show that they are going to be rejected. But when you come to this one, you see that its starting time is after the finishing time of our A1. Therefore, we're going to accept this as belonging to the optimal solution. Okay, so I'm going to mark it in red. Okay, and then now you again recursively call, but this time with this as your current index for k. So we're going to examine the next one, which is going to be k plus 1, k plus 2, and so on. Obviously, the starting time of this again is before the finishing time. The starting time of this is before the finishing time of this one. Similarly, this one. So all these 3 are going to be rejected. So they are colored in blue. But at this point, the starting time is after the finishing time of our current activity. So we're going to accept it. Okay, add it and do a recursive call on the rest. When you come next time, this is your k. So your M is going to start from here. Okay, again, the starting time is before this, before the finishing time of this one. Similarly, this one, the starting time is way before the finishing time of this one, so it's going to be rejected. But here, the starting time is after the finishing time of your current activity, AK, so we're going to accept it. So we're going to reject this 2 and accept this one. And by the time you make this to be your current index, you see that we cannot go any further because we have reached n. So eventually, our set of mutually compatible subset will contain these 4 highlighted activities, the one that I highlighted in red. This is basically how that algorithm is trying to do it. Okay, I hope it is clearer now. Now the final step when solving a problem using greedy approach is to convert your recursive routine to iterative version. Okay, we can't convert the recursive algorithm to an iterative version. It was already almost tail recursive anyway, because if you notice, the only thing left let me just go back to the recursive one just to show you that it's almost tell recursive. Yeah, the only thing after this recursive call is taking the union with this one. Okay, so it is easy to convert this to iterative. It's almost tell recursive. That's what we are saying. So let's continue. Okay, so this is the iterative version. The iterative version actually takes just the two arrays. Nothing else is needed. Okay, let's go through it. So it receives the two arrays of starting time and finishing time. It computes n, no need to be passing n as parameter. Just compute it is simply the length of the two arrays, or any of the two arrays. So you can say s.length or f.length. Okay. Now we're going to use A as our optimal set, the set that will contain the maximum activities. So straight away we're going to initialize that set A with the first activity to finish, which is A1. Okay, initialize K to 1 and now start a loop for M from 2 until N. Okay, having chosen A1, the next activity to look at is number 2. So from 2 until N, we check, is the starting time of activity M, is it greater than the finishing time of our activity number 1? Because initially it is number K, number K is equal to 1. Okay, if yes, then we are going to add AM, activity corresponding to M, to our solution, and then update our K to M, and then repeat the loop with the next M. Okay, but if not, we will just come and increment. You will not add the AM to the set. We will just come and increment M to 3, to 4, and so on, until we find an activity whose starting time is greater than the finishing time of our current activity AK, okay, which we have chosen. So you can see clearly that this loop will actually select those compatible activities and put them in the set A, and that is what we are returning. And clearly the running time of this is theta of n, because it's just a loop involved, and the loop goes from 2 to n apart from this initialization. Okay, now here, as I mentioned in the previous slide, the assumption is the activities are sorted. If they are sorted, then yes, that is the running time you're going to get. You're going to get theta of n. But suppose they are not sorted, then as I said, you can use something like a priority queue. So you will just remove the next priority one. In that case, the running time is going to be n log n. Okay, so add n log n to both the iterative and recursive version in case the activities are not sorted, because you need to do the sorting, which can be done, for example, using priority queue, whose running time is n log n. So if you have n plus n log n, obviously the overall running time is going to be n log n, because this will overshadow the n. Okay, so that is the solution to the problem.